Hello, and we're back. All right. So we're here for the Friday installment. Last one of the week. Of course, I'm recording this Thursday. I want to remind you that Assignment 7 is due online in grade scope by tomorrow evening. Okay, so please do submit that. But the other thing that I got one email about, maybe a couple actually, over time, was that it wasn't the most straightforward thing in the world to see the questions that were being assigned for the assignment, although everyone seems to have gotten there eventually. And I was asked to put them somewhere more visible, so what I've done is I've put them as part of the notes, so I will photograph these today and put them online, but they also asked if I could put them on the blackboard, so I will do that. So that's the first thing for today. Assignment 8. So that will be due Friday, April 10th. Online. Right? And today I will get around to posting. It's not online quite yet at the time of recording here, but by Friday morning, the notes, this lecture, and the assignment, and all that good stuff will be available online. Okay, so the assignment, number 8, is slightly shorter. You'll be pleased to know. So that you'll have more time to finish binge watching, what is it, Tiger King? Yeah, I watched that. That was wild. Man, rednecks are crazy. And anyway, kind of remind, like, I tell you, there's one company that is definitely not sorry about this pandemic, and that's Amazon. My goodness, have my shopping habits changed. But I discovered that, even Amazon has its limits because they do not sell baby tigers. Just in case you were wondering. Anyhow, they sell just about everything else, though, and I've ordered half of it. Okay, so section 4.2, question 2, 4, 5, 10. Okay, and then section 4.3, 2, 5. So let me say a little something here about the sections being covered. So 4.2 we'll start today and maybe finish today. And really, section 4.2 could be summarized thus. The limit laws that you would expect, that the sum of the limits is the limit of the sum of the product is the limit of the product of the limits is the limit of the product, etc. The basic limit laws that you would expect all hold true for limits of functions, and the proof is just the sequential criterion for limits. So we know all about combining limits of sequences, right? Adding sequences, multiplying sequences, dividing sequences, and we have limit laws for those, and we went to some trouble to prove all of those limit laws. Now we want those same limit laws to be true for limits of functions, but they are automatically true for free because we can reduce every question about a limit of a function to a question about a limit of a sequence and then apply the existing limit laws. So in some sense, there's not a lot of content to the instruction in 4.2. And then section 4.3 here, this is a section on, it says some extensions of the concept of the limit. Okay, Those extensions include, what does it mean to take the limit as x approaches infinity? What does it mean to take the limit of a function from the left or from the right, and so on. And question 5 here is in the textbook is just a great big question with 8 parts saying, find the following limits. Okay, so various limits from the right and left, limits as x approaches infinity, but it does not say in the textbook that you should actually prove that these limits are what you think they are. It just says figure it out. Now, just figuring it out, that's kind of Calc 1 stuff, and moreover, in the case of the questions appearing in question 5 here, really easy Calc 1 stuff. So I'm not interested in you just figuring out what the limits are. So instead, I would like you to only do 2 parts. Parts A and D, but with proof. Okay, so I believe that the limit in part 5a is a limit as x approaches 0 from the right, and the limit in part D is a limit as x approaches plus infinity. Both of those kinds of limits have an official definition involving an epsilon or a large positive real number. And I would like you to prove that those 2 limits are what they so obviously are. Okay? Rather than just say what the limits are. So, parts 5a and D with proof. And then finally, question 7. I'll let you stare at that for a second while I get my coffee. Yeah, among the things you can get online are new glasses, which are a handy and useful improvement on the old ones. All right, so I've all had a chance to stare at that. Oh, what was the other thing? Yeah. So the governor just came on TV, and here in Indiana now, kids' schools, have been closed for everything except online instruction for the rest of the school year, and I can tell you, I'm only 2 days into the kids doing online learning, and I am ready to get out of the hotel business. It is no fun at all. I mean, 4th grade, the second time around, just doesn't have the same magic. And I absolutely did not need to remember Brownstead-Lowry acids and bases. I was just upstairs made, downstairs made all morning long. And then the kids want this thing they call lunch. The nerve. I have no idea. But the sooner they get back to school, the better. All right, so there's assignment number 8. Last time, we had finished with this so-called sequential criterion for limits of functions, and we were also discussing what it meant for a function to fail, for the limit as x approaches c of f of x to fail to be equal to a given real number. Could be because the limit fails to exist at all. Could be because the limit exists, but just is not equal to the number L you had in mind. But either way, we mentioned what that looked like. Okay, so I wanted to do another example or two. So here's an example. We want to show that the limit as x approaches 0 of the function 1 over x does not exist. Okay? And as I think I mentioned briefly, if I didn't write it down, saying that the limit does not exist is a shorthand way of saying, i.e., the limit as x approaches 0 of 1 over x is not equal to L for any real number L. Nope. Come on. There we go. Okay, so we have to prove that the limit as x approaches 0 of 1 over x is not equal to L for any real number L. So, in that case, let L in R be given. Okay. So we want to show. So one way to couch this failure of this limit to be equal to L is to find a sequence converging to 0, none of whose elements in the sequence are equal to 0. So something simple, like in fact what we're going to choose is just 1 over n. Okay, so you choose the sequence 1 over n converges to 0, but we're going to prove that the sequence f of 1 over n does not converge to L. Okay, in the way that we show that, let's get to it. So let xn be equal to 1 over n. So xn converges to 0, and xn is not equal to 0. And clearly, since it hasn't been specified, we take the domain of our function 1 over x to be its natural domain, namely all the real numbers not equal to 0. And therefore, clearly, these xn's also belong to the domain of our function. Okay, so this is the kind of sequence we want. Then f of xn is equal to 1 over n, which is equal to n, okay? And we could go through all the details, but I think at this point we're comfortable enough with sequences that we can say the sequence xn, the sequence whose elements are just the natural numbers in increasing progression, does not converge to anything. Okay? This does not converge to L. Okay? So, right, to recap, we want to show this limit does not exist. What that means is for each real number L, we have to prove that the limit is not equal to L. What that further means is that for each real number L, we would like to find a sequence xn in the domain converging to 0, not equal to 0, such that f of that sequence, in other words, 1 over that sequence, does not converge to L. And since our function is so straightforward, we are able to get away with the same sequence for every L. Okay? So it doesn't matter which L you choose, this same approach will work. It will always produce a sequence that does not converge to L. So that shows you that this limit does not exist. Okay? All right. And, if you're an allergy sufferer, if you have asthma, like I do, you have my sympathies, because now things are starting to grow here in Indiana, I'm not a fan of things growing in general, pave the world. But they're starting to grow. And of course, with that comes a little bit of asthma, which, when you're in the midst of a global pandemic caused by a respiratory illness, is a little nerve-wracking. So I went on a run yesterday, and I think I got coronavirus at least 3 separate times. But I've recovered nicely, and I'm here to teach you. Or, well, as my colleague Rolf Turner used to say, when I asked him how teaching went, he would say, "Andrew, I don't teach, I lecture. You can't call it teaching if no one's learning." Just terrible. But I don't know, was I mentioning to you guys that YouTube does actually have stats? You know? So, not only do I get to see how many times you view the video, but I also get to see the average length of viewing, which, actually, it's crept up over the course of the past couple of weeks, and we're now up to like 13 and a half minutes. That's the average before people need a break for a, I don't know, like a Snickers or something. Okay. All right. So now we're on to section 4.2. Limit laws. And they choose this point, for some reason, to introduce the notion of what's usually called local boundedness for functions. I mean, I think the reason they introduce it is that if you were going to go ahead and prove all of the limit laws that we're going to discuss sort of with your bare hands from the definition of the limit of a function, then you would want to have in hand a definition of local boundedness for functions. It would come in handy when you were looking at, say, the limit of the product of two functions. Just like the boundedness of a sequence came in handy from time to time when we were trying to prove things about sequences, okay? But anyway, it doesn't really get used because they wind up proving the limit laws in the way that I mentioned earlier, namely by just appealing to this sequential criterion for limits and then just saying, well, it works for limits, so it works for functions. But, nevertheless, I have the following. So let A be a subset of R, F be a function from A to R, and C a cluster point of A. We say F is bounded in a neighborhood okay, of C if there exists two real numbers, delta, which you think of as small, and m, which maybe you think of as big, both greater than 0, such that what? Such that the absolute value of f of x is at most m if x belongs to, well, the domain of A intersected with the neighborhood of radius delta around the point C. Okay? So when all is said and done, all this is saying is that f is bounded in a neighborhood of C if you can find a small little circle around the point C and a great big number, capital M, such that on that little tiny circle, the function's absolute value never gets bigger than M. Okay, so it doesn't go too crazy. Let's have an example. And leave that definition down at the bottom while I So f is bounded in a neighborhood of C if there is delta and m greater than 0 such that the absolute value of f of x is less equal to m any time that you are inside this little neighborhood of radius delta around C and you are inside the domain of f. Okay? All right. So, let's see. For example, let's take f of x equal to 1 over x and we'll just point out that f is not bounded in a neighborhood of 0. Okay? And the reason is that, no matter how big a capital M you take here, no matter how close you get to 0, you can always find a value of x such that f of x is bigger than that number m. Okay? So this thing fails to be bounded in a neighborhood of 0. However, it turns out that this function, for any other point other than 0, this function f of x equals 1 over x is bounded in a neighborhood of that given point. And the reason for that is quite general. It's because the limit of the function f of x equals 1 over x exists as x approaches any non-zero point. And indeed, we proved that in one of our lectures in the case that you're approaching a point which is strictly greater than 0. And a small adjustment of that argument shows the same thing is true when c is strictly less than 0. So, that's the next result. In fact, so we're going to codify that in general. So, theorem. If f is a function from A to R, C is a cluster point of A, and finally, the limit as x approaches C of f of x is equal to, say, L, then f is bounded in a neighborhood of that cluster point C. Okay? So if you have a function and it has a limit as x approaches c, then f has to be bounded in that neighborhood of c. Its behavior cannot be too wild. Okay? So let's see why that's true. Oh, yeah, where'd it go? Oh man. So, I mean, like I said, the governor has mandated that the kids are now staying home for the rest of the school year. Not only are they staying home, they're staying inside. You know, it's like that. Oh gosh, it's the movie Watchmen. Yeah, they kind of look at me like I'm not locked in here with you. You are locked in here with me. Right? So anything that can divert them is welcome. And my mom kind of saved the day for the time being. This bad boy right here. Look at that. So, I mean, one of the things that depressed me the most about this was that this is the part of the 20th anniversary edition of Lego Star Wars. I mean, I remember, because I was in my 20s at the time, when Lego Star Wars came out, and I was like, man, I wish they had that when I was a kid. Star Wars has been out since forever. You know, since I was knee-high. But yeah, they're 20 years in. But it was just, I don't think they really thought about it, but this is kind of the most badass set they could have gotten. Like, every jerk wants the X-Wing fighter. This is way cooler. Boba Fett's bounty hunting ship. As evidenced by The Mandalorian, right? I mean, they chose not to serialize any other characters. They chose instead to serialize absolutely the coolest, most badass character in all of Star Wars. Anyhow, so it comes these days, you know, why when I was a boy you dumped the box of Legos out and there was absolutely no organization to it whatsoever. You just had to find everything on your own. These days, you know, that's you get your handheld, so everything comes out in a bunch of numbered bags. But this has an advantage. It means that you can ration the diversion. So, out of the 8 bags, they are allowed to put together 1 bag every day after dinner. Rationing. So it kind of keeps them busy for a little while. Alrighty. So order some Lego for yourselves. Treat yourselves with that stimulus check. Alright, so we want to show that if the limit exists as x approaches c, then the function is bounded in a neighborhood of c. Alright, proof. So we will suppose then that the limit as x approaches c of f is equal to some number L, and let epsilon be equal to 1. Okay? So the idea here is that it's not so important how close we are to L, just that there's a limit to how far away from L we can be. And what we're going to do is use the definition of the limit to find a little neighborhood around C where the value of f is no further away from L than 1. So, find delta greater than 0 such that... Okay, now I've got to erase this. Such that f of x minus L is strictly less than our epsilon, which is 1, if the distance from x to c is not 0, but is no more than delta. Okay? So from this expression here, from this inequality, I'll remind you that one of the consequences of the triangle inequality tells me that the absolute value of f of x minus the absolute value of L is less than or equal to the absolute value of f of x minus L, which is in turn less than 1. Right? So if you recall, the triangle inequality says that the absolute value of this difference is greater than or equal to, in fact, the absolute value of this difference over here. Whoopsie daisy. Is equal to the absolute, this quantity here is greater than or equal to the absolute value of this difference over here. And so in particular, it's certainly E greater than or equal to the difference, okay? And then that's in turn less than 1, meaning that for such x, the absolute value of f of x is then strictly less than the absolute value of L plus 1. Okay? So we've proved, using the definition of the limit, that if the limit exists, we can certainly find a delta such that for all values of x that are within delta of c and not equal to c, the absolute value of f of x is indeed bounded. It's bounded by this number here, absolute value of L plus 1. The only little wrinkle left to take care of is that in the definition of being bounded in a neighborhood of c, it does matter what the value of the function f is at c. And there's nothing that says that the function f has to be defined at c. Okay, so a simple example being this situation we've looked at with the function 1 over x as x approaches 0. 0 is not in the domain. F is not defined at 0. But it still makes sense to talk about the limit as x approaches 0. So we don't even know if the function little f exists at c. And if it does, we have to make sure that we account for whatever value it might take at c, because it's a little bit like one of these situations in Calc 1. Maybe is there room to make a little picture? Like, remember these sorts of pictures where you have a function that's, they say it's not continuous because it's missing something here. This hole a little bigger. There. Okay, but the value of the function is defined to be some funny value, maybe way up high. Okay, so in that case, if you look in a neighborhood of whatever x value is down here, then yes, the function is bounded if you get close to that x value. It doesn't get too far below here, too far above here, except what happens right at the particular value of x that you're interested in, where things get kind of haywire. So we have to account for that. So one is the possibility that a little f is not even defined at c. The other is the possibility that it's defined, but maybe it's something kind of crazy, and that needs to be accounted for. So let's do that accounting. So we have, let's just write down what we have so far, that the absolute value of f of x is less equal to the absolute value of L plus 1 if x minus c absolute value is bigger than 0 and less than delta. So then we have two cases. So if f is not defined at x equals c, then we want this number, so the idea is that we want this number capital M such that the absolute value of f of x is less than or equal to capital M for all x that are close to c, whether or not they're equal to c. You know, all the boundedness, local boundedness stipulates is that these points should be close to C, and if C happens to be in the domain, they should include C as well. So if f is not defined at x equals c, we're going to set our number m to simply be equal to the bound that we already have, absolute value of L plus 1. And then the other case is that if f of c exists, we want to make sure that whatever number, capital M, we come up with as a bound for the absolute value of the function little f accounts for the value of little f at c. So if f at c exists, instead we will set capital M to be equal to the max of two things. One is the absolute value of f of c, that's the new information, and the other is the absolute value of L plus 1. Okay? All right. Now, to conclude, the absolute value of f of x is less than or equal to m if x belongs to the domain intersected with the neighborhood of radius delta around C. All right. Well, that's the end of the proof. That's local boundedness. How you doing? Wow. Okay, so this is one of those days where it's just taking a lot longer than I thought it would to get to what I wanted to do. But anyway, the notes will put you slightly ahead for Monday, I guess. So my kids now have e-learning 3 days a week. And while it is kind of a pain, because now, of course, I'm, their teacher in addition to the hotel manager, I will say that I tend now to put pants on 3 days a week, which is definitely an improvement, So, I don't know how you guys are doing on that front, but one industry that is really going to get hard hit by this whole thing is textiles. Because I've discovered that I'm perfectly comfortable in 2 functional outfits. I've got like one outfit for running / working out, and basically the other outfit is something halfway reasonable that I wear to make these lectures. And that's it. And it turns out that that's really all you need. I mean, there needs to be a company that just makes one sort of incredibly, the ultimate custom fitted super duper just made for you jean and shirt, out of the highest quality, most durable imaginable material and stitching. And that way you never have to decide. You just get 2 of each, 2 pants, 2 shirts, you're good. I think society's going to change in a lot of ways when we're done with this. Alrighty. So that's local boundedness. Now, finally, we get to the title of Section 4, which was limit laws. Okay, so we'll summarize things with a single theorem. So, as usual, let A be a subset of R see a cluster point of A, B, just some random real number, F and G now are going to be two possibly different functions, likely different functions, from A to R. Okay? And of course, the limit laws are going to be ways to combine these functions. So suppose the limit as x approaches c of f is equal to L, and the limit as x approaches c of the function g is equal to m. Suppose that those things are true. Then I think I might have done this. Yeah, okay. I'll try and do it in the same order I did it in the notes. Let me briefly consult the notes here to make sure I'm doing it in the same order. Yeah. Okay, so the limit as x approaches c of the sum of the two functions, well, that's the sum of the two limits, L plus M. Again, surprising no one. This is stuff you know from first year calculus. Okay. Part 2. The limit as x approaches c of some fixed real number times f is just that same fixed real number times the limit. So the limit of b times f is b times L. The limit as x approaches c of the product of the two functions is the product of the limits. The limit as x approaches c of fg is equal to L times M. And then finally, the limit as x approaches c of the quotient of these two guys is equal to L over M if M is not equal to 0. Okay? So those are the 4 basic limit laws, the ones you would expect. Okay? And then about the proof, there really, like I said, there isn't much to say. I will just point out how it goes for part 1, and we'll call it a day, because I realized when I was looking at all these videos that I'm pretty consistently a minute or two over time, which probably annoys, well, I was going to say it annoys the heck out of you, but since the average viewing time is 14 minutes, apparently you're annoyed way, way before you get to the 51-minute mark. So let's take the proof of part 1. So the idea is you just say, well, the limit as x approaches c of f plus g is equal to L plus M if and only if we use the sequential criterion for all sequences xn converging to c with xn not equal to c, the limit of f of xn plus g of xn as n goes to infinity is equal to L plus M. right? So this is what we want to be true. This would be enough. But this is already true. We know this is true. Why? Because here we have the limit of the sum of two sequences. And we know that because the limits of each of f and g exist as x approaches c, it follows that the limits of each of these two sequences, f of xn and g of xn, exist and are equal to L and M respectively as n goes to infinity. That's the sequential criterion for limits. And then we know that the limit of the sum of two convergent sequences is the sum of the limits. There it is. Okay, so this whole statement here that we want, that will suffice to prove the thing that we want upstairs here, is in fact already true, or at least we already know it to be true, because it's just a statement about taking the sum of two convergent sequences, and we know that that works. Okay? So I would just say this works. By limit laws. For sequences and then I would just say similarly for parts 2, 3, and 4. It's exactly the same argument. You've got some statement about limits of functions, you translate it into a statement about limits of sequences, and then you observe that that statement about limits of sequences is true because you've already proved that for sequences. Okay, so in other words, the limit laws for functions follow from the limit laws for sequences through the magic of the sequential criterion for the existence of the limit of a function. And that will take us into the weekend. So, do nothing, wash your hands, and we will, maybe we'll pencil you in for 2021 or something like that. All right, take it easy.